Hi everyone, my name is Jean-Philippe Lessard. I'm the new Deputy Director of Scientific Programs here at the CRM. The Director, Louis Vinet, cannot be present, so I'm in charge and I have the honor to present today the first Aisenstadt Chair of 2020. This chair is within the program Optimization 2020, which is organized by Andrea Levy, Fabrice Marcotte, and Marguerite Carvalho, and I would like to thank them for their organization and their energy, and that's because of them, people like them, that we have pleasure to have activities like this. Okay, so before introducing the speaker, I want briefly to describe what the Aisenstadt chairs are. So they are unique in Canada, and they allow the CRM to welcome world-famous mathematicians to spend some time here for periods ranging from 1 week to several months. The recipients are welcome to give a series of conferences here at the CRM, and they are also invited to write a monograph in the CRM monograph series being distributed by the AMS. Okay? So that's a short description of the Aisenstadt chairs, and now let me introduce our first Aisenstadt recipient of 2020, d'ÉvaTardos. She's a theoretical scientist, computer scientist, and a Jacob Gould Sherman Professor of Computer Science at Cornell University. Her research interests are algorithms and game theory, namely games on networks and simple auctions. She has been elected to the National Academy of Engineering, the National Academy of Sciences, and the American Academy of Arts and Science. She is an external member of the Hungarian Academy of Sciences, and she is the recipient of a number of fellowships. I'm going to name a few, not all of them because it's going to take a while. She was awarded the Ferguson Prize, the George B. Danzig Prize, the Van Gatten Award, the Godel Prize, the EATCS Award, the IEEE John Feynman Award, and obviously the 2020 Aisenstadt Chair. So without any further delay, it is my pleasure to welcome d'ÉvaTardos as our new Aisenstadt Chair.
Thank you so much. Thanks for the nice introduction and the honor, and also all the people who showed up from across town, all kinds of places. Thank you very much. I guess I want to tell you a little bit about the direction I have been following for the last number of years now, a couple of years, that sort of builds on both the network team and the game team, but somehow picking up another feature of recent science, this sort of learning, and think about agents that learn. I guess this is built out of joint work with a number of people. Maybe the lead other author of this paper is my student Theodoros Likaris, who's currently in a postdoc in Microsoft Research and soon will again be on the job market. But there are also other students like Vasily, who actually is more permanently at Microsoft, my colleague Kartik Sridharan, and my ex-colleague Denis Nekipolov, who now works at the University of Virginia. So I guess the prime example I want to use in this talk is routing as my sort of games and networks example. And I guess I'll come back in a little bit of which one I really mean seriously for the game we're discussing. But at the very high level, if you want, you can think about it as a car traffic routing game, that is, where each interested participant in the game owns a car and would like to get to work in the morning as fast and efficiently as possible. But if you want, you can think about it as a packet routing problem on the internet, where every time you want to read something on the internet, the packets need to make it from wherever that information was available to your computer. That's also is a routing problem. And I guess what I want to talk about has some connections to both in an abstract mathematical model. The basic model here is that cars or packets will attempt to get to the destination as fast as possible. So the single objective function they have is the speed at which they get to the destination. And I think of it as a game in the sense of if there's congestion someplace, a lot of other cars, a lot of other packets, this does slow you down. But a game in which the players do not intend to hurt other guys. They just want to get their destination fast. So the objective is not to cause traffic congestion or get other people to slow down. Rather, they just want to get to their destination fast. One way it's going to be different than something I have done, or maybe most of us have done over the last couple of years, is that I really want to be serious about that the traffic is not a steady state. So it's not an Nash equilibrium analysis, for those of you sort of ahead in the game theory. It's not a steady state, and that the traffic streams are changing. This is definitely true for packet traffic. When you're done reading the New York Times in the morning, you stop getting packets from the New York Times website, but maybe someone else starts reading something else at that point, or maybe not. So the traffic streams on the internet definitely is a changeable object. Car traffic also has this at a much, much slower time scale. Sometimes something happens and lots of people driving someplace and other places, and less so in other times. A different application that's in the related papers are also discussed, and I'm going to less emphasize but might be more appealing to different of you, is advertising auction. Advertising auction is definitely one of these repeated games. If you know anything about what Google or many of these online service providers live off of, is that they're placing ads in front of your eyes. The value for one of these ads is fractions of cents, not even a full cent usually, though some of them are up to $1 and a couple of dollars, but still. But yet, big companies like Google live on this money. But that really means that there's so many of them happening that they actually run a whole economy. And in particular, it's definitely a repeated game. Like one time you send, play for one of those ads, it's again a fraction of the cents. It's not so valuable, but there's so many of them that it becomes very valuable. And like in other case, there is some sort of changing system going on there. Certain trends in real life cause certain ads to become very valuable or not so valuable. People look at certain things or don't look at certain things. The advertisers, if you want to sell sneakers, when you're done, then when your sneaker production is lagging behind, then you maybe don't want to sell them so much. When you have a lot of sneakers, you do. So your incentives might change. Again, like in the traffic routing system, it's a somewhat changing system. I'm going to come back of what kind of changing systems can I say positive things about and what can I not say positive things about, but maybe at the very high level it's worth saying already at this front that what I'm going to think of is a game that repeats very, very frequently, but the change is happening in a little bit slower time scale. And I don't mean that the system is steady for a long time. I just mean that a single individual doesn't change its intent or behavior very often. If you read the New York Times, you're probably going to read an article, and that will take you some number of minutes to read. If you live someplace and want to go to work someplace, it's probably not just that morning you do that, but sort of a number of times in the morning. And the same here, when you're advertising for something, you don't advertise it 1 or 2 ads. You want to put in a stream of ads. But there's so many of us that there are changes happening every single second. It's just sometimes I'm changing and sometimes someone else is changing. So that's the kind of system I had in mind. Because I am a mathematician, at least maybe trained as a mathematician in any event, I want to turn this repeated game thing into mathematics also, and I'm going to think of a discrete repeated game. So by which I mean games repeat over and over, they're time periods, maybe numbered 1, 2, 3, something. Every period, every player does some sort of action. I call it action I for player I, and then something will happen based on this action, and they're going to keep repeating it over time. And I guess I'm going to think of, which I think is maybe a reasonable objective both for the packet routing and for the ad auctions applications, that the players' values are additive over time. So in the ad auction case, you just want to maximize your income or value on this. In the packet routing case, you're maximizing average delay. That's what this means. Average delay is indeed a standard measure in systems. And again, I guess the sort of main assumption, which is in the title of the talk that I want to take learning, I want to assume that players want to learn from data what's best. That is, react to what's happening in the data stream. This is valuable in every application where cost of individual action is not very painful or not very consequential, but the cost overall is very high. So definitely true in ad auctions. As I said, the ads are fraction of cents, so experimenting with them is fine. It's also true in packet routing. The systems are very well set up for a lost packet. Just resend it, not that big a deal. Overall, of course, we need it to work really reasonably well. Maybe works reasonably well in car traffic also. You know, some mornings you can afford to experiment and try some new routes. Maybe less sure. And what I'm going to ask as questions, and this is maybe why I'm focusing on routing and not on adductions, is not how much money you can make as Google, but rather how well society works. So the question I'm asking is a social welfare question and not a revenue question. And in fact, in a traffic routing, there's no money, so there wouldn't be a revenue question asked. And maybe last, an important extra feature. Remember I said that the system is changeable, so an important question is, how stable does it have to be before we can make positive statements? What is a positive statement here? A positive statement would roughly read as follows. If every player is doing a decent job trying to learn from data, the overall system will work well. That is, I do not need central coordination telling everyone which way to drive to work. They're going to figure this out, and it's going to work reasonably well. So that's what I hope to tell you, and I hope to tell you that in some cases this will work well. To give you some background of where sort of the background or the hope for this, I guess our community, and ours is a bigger community, including some members of your community, such, for example, Adrian Vetta was one of the leaders in here too, is there's a bunch of these theorems out there that basically says that if you don't do learning, don't do changeable environment, at least you just take the Nash equilibrium of certain games, that those have reasonably high social welfare. So the example game that I have on this slide is a result of mine and Tim Ravgarden's for now, actually 20 years ago, or close to 20 years ago, which says that in the exact same traffic routing game, you can make something of this form, a theorem. Maybe very roughly reading this off would say that if you take this traffic routing game where people or packets or cars individually choose the best route and they reach a Nash equilibrium of this game, if the system is designed to tolerate the double traffic rate, so Ri is the rate of the sourcing traffic, I's form of sourcing traffic, if the system is well enough designed or well enough equipped, so it could actually, in an optimized fashion, tolerate double the traffic rate, then in Nash equilibrium, the traffic will be reasonably efficient, or more efficient than the trouble traffic rate would have been in an optimized fashion. So maybe as a sort of nice summary statement, I like to give in giving talks those days that if you choose between increasing capacity of the network versus introducing some sort of central coordination, you're better off increasing the capacity. It's more efficient to increase the capacity than to centrally coordinate the traffic. What I'm going to think about is in this notion of price of energy, which originally was suggested in this form by Koutsoupias and Papadimitriou, which is this trade-off that is comparing the worst Nash equilibrium against the socially, or a Nash equilibrium against a socially optimum solution. And again, our goal here is exactly the same comparison, except I will give you a much worse comparator on the top part. I'm going to think of not a Nash equilibrium, but a repeated learning outcome, where there are many, many handicaps. It's not, they didn't reach stability, so they're sort of changing all the time. And in fact, the environment is so changeable that they couldn't possibly reach an equilibrium or reach stability. It's not clear what it is, so that social optimum cost is sort of a very unreachable benchmark. A social optimum every time realizes that this person stopped sending and we can reuse his pass instantaneously. The learners can't discover it so fast. So in a way, it's sort of a higher or more hopeless benchmark, but that's the goal, what I'm going to try to do. I should admit to you that you can say that this factor of 2 here is not your favorite number, and doubling the capacity is like a big increase. And you would prefer a version where I had to only increase the capacity by a teeny bit. And I agree with you, I also would prefer that. But at least in this lot of literature, I guess I should think of, you know, okay, 2 is not such a small number, but it's a number. It's not something that deteriorates arbitrarily with the size of the network. So in contrast to something like usually named as a tragedy of the commons, it's a very simple mathematical model of a story in an English pasture with cows, where the statement is the more players are in the game, the worse it gets. It deteriorates not by a factor of 2, but with n players, it deteriorates by a factor of n in a super simple mathematical model.
Is this theoretically a thing that your old theorem would no longer be true if you replace 2 by anything smaller?
Say it again?
If you replace 2 by anything smaller, is there some theory that it would no longer be a true theorem?
Yes, this is stated with 2. If I replace this number 2 with a smaller number, I do get here something, actually, but there is a multiplier. So to be very concrete, if I have 1 plus alpha here instead of 2, I get 1 over alpha on this side. I have to multiply it with 1 over alpha. So there is a smooth deterioration as you went beyond 2, but the particular statement's only true with the 2 itself. Where I'm coming from is that over the many years, there's a whole bunch of theorems out there in various setups. These ones on this slide are all versions of some things about traffic, where the community has proved, I think, very nice price of energy theorems. That is, theorems of the form I showed you with constants in them, like the factor of 2. I guess some of these numbers are a little bit better, some are a little bit worse. That selfishness makes the solution deteriorate in Nash equilibrium by some factor. There's a whole bunch of them in the auction kind of setups, and there are many more out there. And again, I showed you all things which have nice constants on them, nice from a computer science theoretician's point of view. 2, 1.5, 3, stuff like that, not deteriorating with the number of players, not deteriorating with the size of the network, not deteriorating with any parameter around. It's an abstract constant. And what I want to do is take these setups, things where Nash equilibrium would be reasonable, and try to say that something of this form, and this is my model of changing game, and I guess the 2 co-authors here is, at this point, both of them my ex-students, and both work for Microsoft at different labs right now, Todoris Sirkanis and Todoris Likaris and Vasilis Sirkanis. And I guess the model we're using is this. We call this a dynamic game. There's a repeated game over and over, and every iteration, every player with some probability p, and I'm going to tell you again what p can be, some small probability. Every player independently decides that, yeah, I'm done. I read my enough, I'm done. And it gets replaced with an arbitrarily other pair, and that arbitrary replacement is not randomized, it's worst case. It can be anyone. So what's happening here is that while everyone is in the game roughly wrong enough, because they only get vanished with a small probability, it's an expectation, they stay for a reasonably long time, there is always change happening. With n players, the expected number, capital N players, the expected number of changes is capital N times p. To get some sense of what parameters I'm going to end up with an n-size n-node graph, can bring the probability p up 1 in log n, roughly speaking. So everyone will stay in order log n steps, parameterized by size network. And I don't care what big a population is. The population can be arbitrarily big. So there is always change. There's lots of change all the time. But everyone stays some decent amount of time. And under these parameters, I'm going to be able to show that the price of energy theorems stay. That is, if they're learning, they're reaching equality roughly similar to what price of energy was trying to give you. Yeah.
When you say arbitrary, do you mean that they have the knowledge of one of the other players already in the system, or do you mean that they come in completely fresh? I don't quite understand.
Okay, he's asking a very good question that I was going to push a little later, and maybe I'll give you a short answer and come back to it in a second, of what do I mean by learning. And I guess he means, what information do you learn from? And the very minimalist way, you definitely, and that will be very necessary for anything I can prove, have to have your own experience. That is, you should, if you choose a pass, then you know how many minutes it took you to get there. That is an absolute minimal basic assumption. If I give you more assumption, more ability to learn, I can, like, so in all honesty, if I give you this little feedback, then this number should be a little bit bigger here or smaller. So I mean, I can't, the turnover probability is optimized for what would be a full information game. So in the traffic routing version, you choose a pass, you experience the delay you experience, but actually you listen to news afterwards and you knew what would have been a good thing to do. Or you opened your Google map and you saw that the other pass would have been better. Depends on how much feedback I give you. You can learn faster and slower. And I guess a line here that I didn't read out, but in reacting to you, I should. I guess the parameter that's sitting here is how much time do you need to learn from data? So the format of learning, I'm going to come back and talk about it in a minute, and I will not go on the details right now, even though that line is on the slide. But one important thing is, even if the environment is super steady, and I give you some minimal amount of feedback, then it will take you a while to figure out what is the best path, what is the right path to choose. Given however much information I give you, I need to give you enough time to learn. And yes, I feel like I'm doing something sort of cheaty here, and will change the environment, and yet my benchmark here is how much would you learn how fast would you learn if the environment would be stable, and yes, that's what I mean. I need to give you enough time that on a stable environment you would have been able to learn with the information feedback I gave you. So I can live with various forms of feedback, and I'm going to have to adjust this parameter that in expectation everyone stayed long enough, that had the environment been stable on his life, they would have been able to learn. Does that somehow roughly answers what you're asking here? Okay, so I'll come back to these parameters and what do I mean by learning. I want to actually start to talk about learning, and I want to start maybe a little bit more back than where you wanted to start. Learning and games has an insanely long history, which in particular here means before I was born, which I know is way before many of you were born. And I guess it leads back to Julia Robinson, who I think is the first to think about it, repeated games repeated play of games. I guess she had a particular form of of learning in games called fictitious play, which I won't emphasize exactly what that is. The interesting part is that the question she asked, and the question game theoreticians often still today ask, is thinking of learning in game as a pre-play. That is, that's not the real thing. This is like auction, like high-priced auction. I don't know how many of you know about the incentive auction that the U.S. ran, I think, a year or 2 years ago on selling wireless communication for cell phone companies. Those kind of things are one-time opportunity in every 10, 20 years. Some countries selling bandwidth in auction. 2 years ago, it was the U.S. that did this. They set up an auction system, and every company who wants to bid, they offer them practice opportunities. They run practice runs of the game. You're not winning anything in this game. They just have to practice how to play in this game. So that's the context when Julia Robinson was thinking about auctions. There are these practice runs. You're running some sort of learning algorithm in the practice run with the hope that the practicing will help you find the Nash. So when the real game comes, you're going to find the Nash equilibrium. So a lot of this literature focuses on what does it take to get the Nash equilibrium, what learning algorithms find the Nash equilibrium, what games can learning find the Nash equilibrium. And there are a couple of theorems of this form, most dominantly maybe 2 or 3 of them. The 2 early ones, or the earliest one, Julia Robinson proved that in 2-person zero-sum games, learning does find the Nash equilibrium. There's an extension with non-two-sum, but still 2-person, 2-strategy games, a very limited, restricted set of games. And really, at the high level, the answer is nope, learning does not find the Nash. So what does it mean when learning finds the Nash? learning finds an edge. I think of it as something like this, and maybe not quite this, but at least converge to this. They play something for a while, and eventually they get to a situation where they find a sort of one-shot, something that's stable. And I mean, really, they meant converge to this rather than actually find it, but roughly speaking. This is what it means to me, Nash, and I'm using this slide also to sort of introduce the notation. So this is the cost in this game. For player I, had they played this strategy vector A, which is indexed with the different players. And this is cost of player I if he or she individually deviated to some other strategy X, everyone else is playing this strategy A. So if this inequality is true, it's not beneficial for them to deviate to other strategy X, and I'm going to call this the no regret inequality. The player I not regretting that he went along and played this Nash equilibrium A, and indeed this is the Nash equilibrium definition. So that's what Julia Robinson and that whole community was hoping, that learning will lead them to a solution like this. Now, here the one sort of data set that I will show you, and indeed this is from adductions and not from traffic routing. There is no sense that this is happening out there. This is bits on adductions on a couple high volume, high value, very frequent bidders. So these are bidders that change their bits multiple times a day, or attempt to change their bits multiple times a day. They have insanely large budgets. They have a lot of money, and it's very important for them, at least from their behavior. And this is what the bids do. And some of them seem sort of stable-ish, like these long ones here is wiggling on the bottom, and some are very non-stable. And if you want to think about why this is happening, I mean, everyone knows that, or at least most people in the industry do, because there's these companies out there. Either you're a big company and you have a machine learning department that's optimizing your ad placement, or you hire someone, and these are two companies you could hire to do this for you. And if you think of what these guys do, pretty clearly they advertise it. They're using AI or machine learning to optimize your bid. And if I look at what these curves look like, they totally look like gradient descent to me. Someone is optimizing a function in a gradient descent setup, which is what machine learning usually does. So it's a very good match that what they're doing is using machine learning to optimize their bids. So what I want to do is actually do this sort of change of objective, a change of focus, and think of games where the learning phase and the play phase is not separated. This is not like next year we're going to run an auction and this year we practice. But instead we're running the things and we're learning on the thing that really makes the money. And I don't hope that they're going to find the Nash equilibrium because they don't. But instead I want to say, how about they reach a property which is often goes under the name no regret property that's like a Nash equilibrium except there's no requirement of stability. So this is the no regret property. It goes under the name of no regret property, which says that, you know, this would be a Nash equilibrium version, and then, this is the version without the, Nash equilibrium. You play different things at different times, so the A's I have to now index with time. And what you're saying is what you paid is definitely better than a single strategy with hindsight. You know, maybe every iteration you should have done something different, but there wasn't a steadily good thing that you didn't find. So I guess what this would say in the traffic routing business, that it could be that driving on one highway on, you know, odd days of the week is better than on even days of the week. The other one is better, or on, depending on something non-predictable, which is hard to know. But if the highway 99 is better on most days of the week, then please wake up to this fact. And this is for reality and for maths, I'm going to put in a little error. Like as you learned, you're not perfect, but you're at least pretty close to this. So this is called the no regret property. What's nice in the no regret property is that there are plenty of algorithms out there and very simple algorithms that achieve this property with small error rates. And they do very natural things which you wouldn't surprise that that's what you should do. Watch what's happening and try to higher probability play the things that were better in the past. Very natural algorithms that achieve this property. I have a couple of slides here which for lack of time I'm going to skip, but maybe just summarize on what exactly happens in this game if you try it on rock, paper, scissors. So as I said, it's not converging. learning does not converge to Nash equilibrium. And in fact, in particular, it doesn't do that on rock, paper, scissors, and it's a good game to try. Instead, it's going to somehow do some sort of funny correlation in which our behavior becomes correlated because, and that's maybe the message that's worth taking home, if I play rock, paper, scissors, maybe any two of you here, then we're all learning from the shared history. And the shared history will serve as a correlation device. We somehow will behave, somehow we end up correlating with each other because our source of information is the same. So it helps to correlate. There is this notion called correlated equilibrium, which I guess is defined in which the outcome of this kind of game playing. It's almost like Nash equilibrium, except the players can get correlated, and was, I guess, maybe highlighted by Hart and Mascolel. If everyone does learning, then the long-term play, average play is converging to a form of correlated equilibrium, literally the same inequality as equilibrium, except the word correlated. We're allowed to correlate with each other. In Nash equilibrium, we have to play independently. In correlated equilibrium, we're allowed to correlate. The classical definition of correlated equilibrium has a moderator who tells us what to do. Here, there is no moderator, but apparently history serves as a moderator. We correlate on our own. Okay. Before I tell you what we can prove, I want to spend at least a couple of minute or two trying to convince you that you should care about this notion of learning. I like learning as a solution concept in game. I like it for a couple of reasons. Learning is doable. I told you there are plenty of algorithms out there that do it. They don't need, and this is a little bit starting to respond to this question, no need for a common prior, no need for assumption. People can know more about the play or less. Some people can be knowledgeable and know a lot, and other people know little. It doesn't matter. Learning is doable. And yes, if you learn more about the game or learn more about who else is playing, you will learn faster. Other people will learn slower. Everyone will learn. It's a doable task. It's a behavior assumption rather than an algorithmic assumption. That is, I'm not assuming that you're running my favorite learning algorithm, which I guess would be multiplicative weight, but other people have different favorite learning algorithms. I'm assuming you satisfy the no regret inequality. It seems so natural. If there was a steadily good solution, please wake up to this. If you're paying attention to life, this ought to be true. Again, I probably don't have time and we'll skip through those slides, but I have Microsoft data to show that these guys do seem to satisfy the no regret assumption pretty closely. So I don't think they're running any of our algorithms. In fact, I have good evidence. They're not running multiplicative weight. But nonetheless, they satisfy the assumption because it seems like a very decent assumption. And that's this. And then last but not least, I'm a mathematician. It's a nice inequality. I can use it. It's a mathematical assumption. It's very usable in doing theory with it. It's also, there's a bunch of human subject experiments and data experiments out there. I guess the data I will not have time to show you is from this paper, again, using Microsoft adductions. There's other ones here are lab experiments. In fact, if you look at the top line of some of these papers, they mix whether the top line is that the experiment shows that they do or don't satisfy the no regret assumption. In particular, this paper up here from EC 14 was saying that no, these people are recency biased, and that's why they don't actually satisfy the no regret assumption. Humans are too recency biased. I'll come back to it in a second. I think recency bias is an incredibly good property humans have. Yes, what happened yesterday is so much more relevant than what happened a year ago. We should all be recency biased, and recency biased learning is good for us, and I'm going to come back to this point in a second. And that data suggests that they learners are actually satisfying no regret assumption if I'm allowing them recency bias, which is what they have. This is some data showing. So again, this is what I mean. I'm going to now come back to what can I do with this as an assumption. So appropriate, this was the no regret assumption was this. The learning of what the agents have is no worse than a single strategy with hindsight with some sort of error. I, in fact, and had I showed you the data in more details, maybe I would have had a better point in convincing you. I like a little bit better a sort of fixed epsilon version of this, and I'll come back to a version of why I like it in a couple of times in the talk. So this is when you want to prove this, or any of you have seen a proof of how do you get no regret, usually it goes through this theorem first. That this theorem says you pick a fixed epsilon, which is a parameter, and then you can reach an approximate version, not with such a big error, but with something very, very small. So if the D is the number of different choices that people are trying to learn the best of, epsilon is your favorite picked parameter, you get this sort of much smaller regret error with a epsilon, 1 plus epsilon multiplier on the cost. I like this for two different reasons. One is, when I said that these people satisfy the no regret assumption, I mean within 5%. They don't go all the way. And so I want to use this, and I meant epsilon 5%. That's my epsilon, a fixed epsilon. The second reason is that this optimization of your learning, so you get that result from this by picking the right epsilon. There are all kinds of knowledge needed to pick the right epsilon. For example, you need to know the timeline. You need to know all kinds of things. And people tend not to know that. But if I want this version, you don't have to know anything. You just use epsilon. So this is sort of easy, algorithmically easier, needs less knowledge to achieve this band. And also, I think more realistic. Data more supports this with 5%, maybe even 8%, something like that. So that's the version I'm going to use in all my theorems. Again, what I want to show is a price of energy band. So go back to Kitsopias and Papadimitriou. What I showed you first is a cost of the Nash equilibrium versus the optimum. I'm going to give you a sort of two-step process of how I can try to get what we can prove. Step number one is actually going back to an old paper of Avrum Baum, and at the time a bunch of his students, and was very nicely summarized by a later paper of Tim Rovgarden. I guess the gap is actually bigger than this, despite the 1 year only. When you play a repeated game, just like I defined it, periods and repeat, but there's no change in the game. And what that paper shows is that whatever we proved, I guess this doesn't work very well, whatever we proved on this side, at least given the proof techniques we're using, automatically extends to this side, which is really like sort of a beautiful observation. And what we're trying to do is this. We change the dynamic population game, so I guess I have to have both the Nash and the optimum now indexed with time, because, or indexed with values of the players, because the player set is changing. This is what my goal is. And again, what I'm going to offer you is a little bit like what the Tim version of that second theorem is, an extension theorem. If you have a nice theorem on that side, then I can get you this better thing. And I want to give you a couple of minute framework of how does the proof work, not with the glory details of all the bells and whistles included, but rather a high-level feel of what made the theorem true, which I think is something that one can hopefully do, and maybe can get something or enough out of this as a sense. So to do this, I have to go back to the statement I made here between these two, that Tim's extension theorem was that given the framework or how we prove this price of energy theorems, the extension applies, and this is how that works. So maybe not surprisingly, or maybe surprisingly, most of our, or almost all, not just most, almost all, with super few exceptions, the price of energy theorems going on a very, very simplistic framework. Rather than using anything about Nash equilibrium, it's using a single property of Nash that if I take this optimal solution, socially optimal, the best had I designed what they should do, which is person I should do this AI star as the optimal action. The only inequality that's getting used that no one is regretting that they're not doing what they should have done in the optimal. So that's that inequality up there. And this is really set up to make learning really viable, or more honestly, wasn't set up that way, but once this is the proof technique, it's a nice observation that wait, this is something learners satisfy. They don't know what the optimum is, but this is literally the no regret inequality. you're not regretting anything. In particular, whatever the optimum was, you're not regretting that one either. This inequality does not require, you know what the optimum is? It just requires that you don't regret that. Since you're not regretting anything, this is one of the many things you're not regretting. This is the inequality gets used. And then the observation in it's something that Tim named the smoothest inequality, is that there's some funny inequality that tends to be the heart of the proof that you can end up proving. It looks complicated, but it actually is maybe very natural. It, roughly speaking, says something of this form. If a solution A, whatever that is very, very much more costly than the optimum, so this green thing is insanely more expensive than the red thing, then this inequality says that on average, or one of these guys will have incentive to do better. It is somehow putting something of the form that given the lambda and lambda below, above 1 and mu below 0, this inequality says that one of these guys is doing better here in the optimum, and therefore we want to deviate. And indeed, this inequality very easily implies the price of energy bands. Given the one inequality we have up there, the cost at Nash is lower bounded by the cost had they all deviated, and all I have to do is rearrange the inequality and get this band. And the observation here is that in almost all these games where this is a technique of proof, this is actually a sharp band. You can optimize what lambda and mu you're using. If you did a good job at that, that's the truth. That is the price of energy. So this is a very simplistic proof technique, and indeed, it's ideally set up for learning, and one can copy it literally one-on-one. If you don't assume Nash equilibrium, assume that they have no regret learning. I told you one could, because what do I get in learning? Literally the same inequality. They're not regretting the optimum. I go through the same exercise, rearrange inequalities, and get almost the same with an extra little bit of error, where my epsilon and this extra error term at the end came in as error parameters, but it's the same thing, literally the same proof. So what we're hoping to do, and I guess this is the sort of changing parameter version of life I promised you in the beginning, I wanted to live this proof, or live this ID, to a changing environment. So back again, this is our dynamic population model. So every iteration, every time, every player with some probability P vanishes and gets replaced by a worst case other thing. And again, players are, while they're around, they're trying to learn from data. Now, I have to admit, I slightly cheated you. And the first question I should ask, if you're trying to learn from data, could this inequality that we all talked about, this single strategy with hindsight thing, be good enough? And honestly, the answer, of course, is no. And honestly, the answer is no for a reason that maybe that was my whole motivation of starting this project. And sort of maybe start with the example and then what was the start of the project. If you need to learn, if learning is useful for you, then maybe this is what life is like. Some player showed up, and this is a traffic game, and we're going to focus on that red guy up here who's playing for a while. And maybe when he shows up, life is like this. There's a ton of traffic up on like this, lots and lots of people going here. And so he chooses the lower pass because, upper pass is very congested. And then as he stays around, because maybe he ended up staying quite a while, those guys vanish. And instead, some other guys show up here, and he should change. He really should change his strategy. And in fact, this is literally a sentence I used to say about learning before I even started this project, before when I was still working on the team version of the study people. Learning is better than Nash because learners can adjust to changing environments, and Nash does not. But our models didn't support this because we didn't have changing environments, and now I wanted to have it. So I need a version of learning that's actually capable of this. Single strategy with hindsight is not it, because this guy didn't have a single strategy with hindsight. What learning can easily do is this, and this is really easy, and this is where recency bias comes in very naturally. If I want to adjust to a version of changes where a sequence is not the different every day, that's hard, but there are k changes in it. You know, you use the same path for a while, and then apparently construction starts on that road, and you're in trouble. Then you switch to another one. But the number of times you're going to switch is something named k. And then in our version of this approximate no regret with the epsilon included, I guess you get an inequality of this form. This particular form is copied out of our paper from NIP 16, but very similar identical inequalities are in earlier papers too. I guess we like this epsilon version, and the learning community tends not to. And here I have a big advantage because I keep the epsilon fixed. And the reason is that in order for get a similar inequality in the classical one without the epsilon in, you need to know the number of changes ahead of time. And learners don't. If the environment is changing, how do you know? With the epsilon version, you don't. Again, I can pick an epsilon and run this algorithm, and I will get the error band k here, whatever the number of changes was, without knowing ahead of time how many there will be, and I definitely need that version, which is coming our paper. And literally what you need to do is recency bias to learning. Take any favorite learning algorithm that you already have, multiplicative weight if you want, or any of the other ones, and hit it with recency bias. That is, discount things that happened too far away in the past, and they get these bands. Why is this nice? Because it can tolerate changes. What is it that you have to be careful for? The error goes up with the number of changes, so you have to be careful how many changes you're hoping to tolerate. And now I can tell you sort of what one piece that's missing, and maybe get this sort of main message of how our proof works. So if I want to completely copy over the proof hint I showed you from the original learning algorithm, this is what I would wish to have. This inequality would say that the cost of what they're playing against the varying set of other players is no worse than the cost of the optimum compared to the true optimum every iteration. So the comparator, the thing I want to compare to, is the true optimum. And I guess the trouble is the true optimum in real life is a very changeable object. So the number of changes here, which is what I'm measuring my error band, is an insanely high number. And that will be hard. That's too hard. I guess this is easy to convince you probably in any setup, because this is an optimization semester, so all of your optimizers. But just in case anyone is not on board, here is a matching example. Here's the optimum matching. Maybe there are some weights over there for cost of what you're optimizing. One guy went home. What happens to matching? You do an augmenting pass, and everyone has to match to something else. So the matching changed. And one guy changed, and the whole matching changed. And this is unavoidable. This is how optimum works. So what I'm going to want to do is I want a less changing object. I want to compare not to the true optimum, but a sort of, more stable animal, more stable thing. So at the high level, what I hope I gave you a sense that might be provable is a theorem of this sort, and this is our high-level theorem, that whenever you can prove that in a sequence of changing environments, there is a stable, close to optimal solution, reasonably stable, not too many changes, then the price of energy will be close to the price of energy of the optimum. And I guess in addition to the usual price of energy loss, there is a loss here of whatever this A star tilde was. That is how far away you are from optimum for getting it to be stable. Learning to do at least as well as a stable optimum is somewhat doable for learners. Learning to do against a true optimum, which is very changeable, that's too hard for them. But this is doable for them. So I'm missing one piece, and I'm going to only spend 2 seconds on the missing piece. But this is actually sort of what might be closer to home for all of you, and maybe some of you want to start working and helping us giving benchmark theorems in a pure optimization world. So I gave you a slightly changing environments and players, and one of them sometimes vanishes and replaced by someone else. Under what circumstances can I prove that there is a stable optimum, that is an optimum that rarely changes? I guess Oh, I guess before I go there, I guess I probably should have summarized this sort of theorems we're getting here. Again, the changeover also had to do with the sort of learning. People have to stay in the game long enough that they're capable of learning, like I said last time. And then you get the worst case band, which at least for us consists of 3 parameters. There is something called alpha, which is the old price of energy band. So whatever price of energy was at Nash, this can't avoid it. If they're at Nash, then we had that loss. There's a second one, which is an additive error, the regret error. As they're learning, there is an error in their learning, and this plus additive error in the learning. If I keep them in the system long enough, that additive error will go to 0, but there is something there. And there's a third parameter, which I call beta here, is what do I have to do to keep to prove that there is an optimum solution that's close to stable? And that's a third loss. And this third loss is what I want to spend at least 1 more minute telling you about. So I need a theorem that says that in large games with many players, if I keep changing the players at a low rate, there's an optimum where people's optimal behavior, or close to optimum behavior is pretty stable. So I give you 2 hints for how we do this. One, a direct proof, which I think I almost kind of prove it on the slide, even though just 1 slide, making you believe it. And one is really a reference to a whole other literature that other people worked on this. So the proof is the matching, which is why I showed you the matching in the beginning. A true optimum matching is a very unstable object. Any one change causes a whole augmenting path. But here is one that's a much more stable object. Do greedy matching. Greedy is much more stable. Greedy just means, take the highest value guy, assign to the highest value, repeat. If a low value guy vanishes, higher values will stay the same. They're not affected. That's what greedy means. So everyone only gets affected for people valued higher than them. That makes it much more stable. With a little bit of rounding, I can make it super stable, and it's a potential argument, but it makes sense. Why do I like this? Greedy is a factor of 2 off from the true optimum, so I lost another factor of 2 on this. It's a constant, and it made it much more stable. If you don't like losing a factor of 2, here is the whole literature. You can pick up something named differential privacy. I don't know how many of you know about differential privacy. It's a literature whose goal is to generate solutions that the individual player's private data is protected. And their definition of what does it mean its private data is protected is that the solution you guys experience is unlikely or very minimally will change, either not very unlikely with an insanely small probability it will change, depending on whether or not I was in the data set. This is literally what I want. It is unlikely that your solution changes when I go home. Same thing. In fact, I want something weaker than what they wanted, because they wanted an algorithm to generate this thing. I just wanted it to exist. It's in my proof. It's not in my algorithm. But I kind of want literally what they want. And in fact, there is a beautiful literature of differential privacy. I guess the versions originated by Dwork and Cynthia Dwork and Aaron Ross just put out a book on this. The version we're using, which is game theory version, is originated by a paper that Mike Kearns was also a co-author in addition to Aaron and others. And there is a beautiful literature there creating a lot of examples, including traffic routing, markets, and other things, where they can prove that if the game is big enough, there is a stable solution of this form. And they're usually using a small parameter epsilon. This is not a very small loss compared to the optimum for exactly the same price of stability I wanted. That when one person goes home, it's unlikely that the solution changes for anyone else. So I'm going to end here, and I guess sort of what I hope is the take-home message, maybe 2-fold. I really like learning as a model in repeated games, and I think repeated games are interesting object to study. Learning is a good way to adapt to opponent, and actually has another advantage I didn't mention before is if the opponent's playing badly, a learner takes advantage of them. And Nash equilibrium does not. You're not better off if the opponent's doing something stupid at Nash, not in a zero-sum game in an event. Here you are. If he's playing badly, you should win. That's how it works. So that's another advantage. This is not something we can currently support it. But I did prove to you that learning players do well for society. That is, overall, they do reasonably well, even in dynamic environment. And I guess it was 2 parameters. If in games where approximately optimal stable solutions exist, and there's good price of energy band, we can lift it to make it efficient even in dynamic population. And one open question I want to sort of end with is, I used a particularly common and simple form of learning, this no regret, as a behavioral assumption. You can ask, are there other forms of learning that would do a lot better? And I guess one tempting form of learning that I would love to have better results on, something where the learner anticipates what the opponent will do. No regret learning is somehow almost assuming that other people won't react to my actions. And there is one particular form of proposed in a, I think, either NIPS or ICML paper from 2012 called Policy Regret, where I'm trying to take into account, watch what the opponent reacts to my behavior. If I congest this road, maybe you will get off, or something like this. That's an interesting idea. That's a sort of more sophisticated form of learning, and maybe that could do better. And I'm going to stop here, and thank you very much.
Thank you, d'ÉvaTardos, for a great talk. Are there any questions or comments?
You've used several times the parameter D that I think refers to either the number of strategies or the number of actions. What if this is infinite?
So I call it D because, honestly, rather than the number of strategies, I rather to think of it as the dimension of the strategy space. Okay. So in the traffic routing case, that's the number of edges, because the path lives in that dimensional space.
But in an auction, I can
if your strategy space is, infinite in a way, it's a convex things out of a finite dimensional space, then the dimension was still finite. If I lift it to literally infinite, and I guess one example where it could be thought of as infinite is auctions where I can bid any real number. I know what the dimension is. I can lift the theorems by discretizing, like adding a little error parameter for tolerating some amount of error, which allows you to use discrete bids. I don't have a very general. Somehow I have to get it down to a finite dimensional thing. And one of 2 tricks I know how infinite bidding spaces or infinite action spaces can become finite dimensional is one, if they actually live in a finite, like they're real in a convex combination of finite number of things, or live in a finite dimensional space on their own. The way paths in a graph live in the dimension of the number of edges in the graph, that's the dimension of space they live in. Or if I can discretize them down to finite and add a little bit of discretization error. I don't have an abstract theorem that can do this when neither of those 2 things are actionable. I don't know what application you have in mind where, but sort of my prime application, one of these 2 tricks gets it down to finite dimensional.
I was more thinking about the auction setting. But would I be correct to understand that the larger your strategy space is, then the worse the learning becomes?
Yeah. So in single item auctions or like ad auctions, which is like single bid auctions, the still works okay. I just have to discretize the one-dimensional infinite space. The dependence on the dimension is bad. When the dimension is really big, then the log D, which showed up here, becomes kind of problematic, and learning becomes very big. And in particular, one place where learning is doing really badly on the time to learn is horrendously big, and in fact their hardness results is multi-item combinatorial auctions. That is, if you bidding on multiple items, but your value is some kind of weird combination of the different things, then your bidding space is the number of items, discretization to the power of the number of items, which is a very big bidding space. And in fact, there are hardness results of the form that it's not even MP, but sharp P hard to get the no regret, to learn well enough to no regret learning, or will take you exponential time to do that. So this works very well when what you're learning is single dimensional, and works definitely not so well as you increase the dimension. In particular, multi-item combinatorial auctions, this is not. Learning is slow. There are some proposals out there of what else you can do, but I guess, works well when you're in a single dimensional space. You're measuring a single parameter. Yeah.
Are you aware of any multiplayer repeated games where all players cooperating is one of the Nash equilibria or no regret equilibria that you can develop?
Sure, like Adrian's game. Right? The true optimum is a Nash, and therefore, if they cooperate, they can get the true optimum, and that is a Nash. There are few games out there.
I think there's a lot of games where Nash is the closest integration which seems
Why is that? But I guess in a higher level, there are games where the true optimum the social optimum is a Nash. That would work for, like, in any game where the true optimum is a Nash. I guess what you're saying is true. If the true optimum is a Nash, then cooperating, they can get the true optimum, and that is a Nash. And there is I guess in some, there is a long economic history of thinking about welfare and Nash equilibrium. If you ask a classical economist, this is the question they like. And the question I'm asking, then when the true optimum is not actually a Nash, how far off you are? This is something they historically didn't look at, and only maybe more recently our community convinces them to consider it. So there are a bunch of games out there where the true optimum is Nash, and then I guess I don't see anything else where, like, when the true optimum is not actually also Nash, then I don't see how your theorem could be true.
From the cooperating point of view, all of them are cooperating, that's the Nash equilibrium.
Right. So when the true optimum happens to also be a Nash.
cooperating, then you're looking at sort of core strategies, but bigger groups can deviate as well. So they're very different.
Oh, that's a good point. So that might not be strong enough. Like if a subgroup cooperates, they can still get something better for themselves. Example.
Questions?
Yeah.
So, in case the repeated game was not a normal form game but a Bayesian game, in principle, all of your results would apply if I just do the credit reduction, but that comes at a cost of complexity because the action space now becomes the space of mapping from the observation set to action. Have you thought of, are there efficient ways, either in the price of anarchy or the price of learning type of setup, where it was a Bayesian setup and local information could be exploited to speed up the learning processes?
Yeah, so there is Bayesian extension theorems for most of these things. I guess if we go back to the sort of lifting, like the back of the just the price of anarchy word of view and not the learning version, there is a Bayesian extension theorem. So the same proof technique, if it was true in the worst case, it's also true in the Bayesian setting. There we have a NIPS, or which nowadays is called NeurIPS, paper from, I think it was 15 with Jason Hartline and Vasily, where I think we are trying doing what you're suggesting we do, claiming that that the learning is good enough in the Bayesian setting also. I mean, I guess I have to understand what should I mean by a Bayesian setting. So I can do a conversion, multiple different conversions from Bayesian learning from regular. So one way to think of a Bayesian setup is it really is a deterministic game where the only randomness is that only a subset of players are playing. So every iteration for every distribution, I pull the player and then make them play against each other. But then every player plays very rarely, and it takes them a while to learn.
I was thinking more in like the classical Bayesian game framework, where each player gets some local information and has to choose an action based on that, and the game is repeated infinitely often. If I naively use your result, you'll get log d terms, you'll just become sort of...
That's very high. That's very high. Yeah. So we have a paper with Jason Hartline, Vasily, and me that trying to do this, but maybe not fast enough. I think you want something better than what we can do.
Something better
I think what we're doing with Jason and Vasily is current state of the art. So maybe I think you're hoping for something better than what we can do. So his point is that then your action should depend on what your type was, which you discover every single second. So your strategy space, again, that's another way that your strategy space grew up, because it's a function from types to... Yeah, good point. And actually, one thing I should have reacted to the previous question maybe is a good closing. That's another nice open question there, is asked more broadly. This assumes that people are learning, but they're not talking to each other. There is zero cooperation. Like, it doesn't occur to them that to turn to, one of you and say, tomorrow we should together do this other thing. And so again, you can ask the question, having a large community like all the traffic, all the cars in Montreal suddenly cooperate, that's not very likely. But so does something better happens if we allow limited group size cooperation as a form of experiment? It's a nice question that I don't have an answer to, and it's sort of we're touching on the what's up if cooperation is better to do. I guess I wasn't thinking of the whole group cooperation. I was more coming from the other end. Small groups are allowed to try to cooperate. Does it help? Can they help? Can they converge faster if they do that? Can they?
Maybe they should stay in the system less. If they can learn from others in the system, maybe they reduce the amount of time.
They learn faster, and therefore.
They learn faster than to stay in the system less.
I mean, that's one option, or they can converge to a better Nashes. So some of these games have multiple Nashes, and I'm always measuring against the worst possible Nash equilibria, but maybe cooperation allows them to find a better Nash.
Yeah.
Okay, I propose that we start here. There is coffee served in the room, in the ceremony study just behind here. So I propose that we continue some discussions there, and please welcome me in thinking about.
Thank you.